Hello, my name is Sean Goralski, and I'm a PhD candidate at the University of Texas at Austin. Today, I will be presenting my poster, COFforH2, Synthesis of Iron Hydrogenase-Inspired Complexes for Insertion into Porous Covalent Organic Frameworks. This project has been conducted in partnership with our collaborators at the International Iberian Nanotechnology Laboratories. Let's start with the motivation for this project. Here at UT Austin, our main focus in our laboratory is the synthesis, characterization, and catalytic applications of small molecule models of the iron hydrogenase active site. This enzyme active site, seen in the top left panel, is unique in nature and is able to catalyze the reversible heterolytic cleavage of dihydrogen gas to form a hydride and a proton. The reverse reaction is also possible, in which H2 is formed. This is a reaction of strong interest in terms of renewable energy. So we wish to be able to take advantage and leverage the amazing reactivity of this natural enzyme. However, dealing with enzymes can be quite tricky, especially in terms of industrial applications in which its stability and production can be quite difficult. We instead turn to another nanomaterial, covalent organic frameworks, to serve as the macromolecular support for this enzyme active site. My role in this project is to synthesize the small metallo-cofactors, which will be impregnated into these COF materials, which should have hydrogenase or hydrogenation reactivity. So today I have two main classes of molecules. One class is rhenium-based, the other is ruthenium-based. We'll talk about their synthesis and how we plan to introduce them into COFs and some of their reactivity. So first we shall start in the bottom left panel with our rhenium transfer hydrogenation catalysts. Manganese bispyridine tricarbonyls have been known to serve as transfer hydrogenation catalysts for quite a while and are well documented in the literature. We wish to use analogous rhenium catalysts, which should have very good stability, so they can easily be inserted into a COF. I have synthesized two classes of rhenium catalysts scaffolded by anthracene bispyridine ligands, as we can see in this panel. At the 10 position of the anthracene, one has a C12 aliphatic chain, and one, not shown in this picture, is decorated with a propargyl group. This is to serve so that we have two different methods of attaching these complexes to two different COFs. On the left, the C12 appended rhenium complex should have high affinity for the fairly hydrophobic pores of our first COF, TFBBD. This aliphatic chain was inserted by a Grignard reaction, and we have shown, you can see my coworker Cristal's poster for this, that we've been able to insert this into a COF with acceptably high rhenium loading. The model on the right-hand side, we are able to use that alkyne-decorated rhenium complex to attach to an azide functionalized COF via copper alkyne azide click reaction. Our second class of models, our ruthenium-based iron hydrogenase mimics, are quite closer to the actual enzyme active site structure. As we can see, it has the distinctive facial CNS ligation. Based on the design of our previous iron models, I have been able to synthesize and characterize this ruthenium-based iron hydrogenase model. Here we can see in its IR spectrum, we see the distinctive two peaks at 2051 and 1980 wave numbers indicating a ruthenium-2 dicarbonyl. This complex should show quite enhanced stability over its iron counterpart, which is light, air, and moisture sensitive, which would make it quite difficult in our initial studies of impregnating this into a COF material. Finally, I want to talk about the transfer hydrogenation catalysis that we've seen for some of these complexes. Our rhenium complexes have been shown to accomplish the transfer hydrogenation reaction of a ketone substrate, cyclohexanone, to form the corresponding alcohol. This has been accomplished in 81% in the absence of COF. This was an excellent proof of concept to show that this is an effective transfer hydrogenation catalyst. In the future, we wish to determine conditions under which this rhenium catalyzed transfer hydrogenation can occur within a COF nanomaterial and probe it by various spectroscopies. We wish to determine conditions to attach our alkyne functionalized rhenium complex to a COF, and we wish to study more about our ruthenium system and see how closely it resembles our iron system. Thank you very much.